Hello and welcome to Physics with Amol sir. So this video is for class 12 and we are going to continue with electrostatic potential and capacitance. This is part 4. So in the previous class we saw one very important derivation. Okay, that was for the electrostatic potential due to system of charges. I hope those concepts were understood. Today we are going to talk about the concept of the equipotential surfaces and we will talk about potential energy due to a system of charges. Okay, so let's begin. So what we mean by equipotential surfaces? So from the name itself you can see equipotential surface, equal potential. So any surface that is having equal potential at all the points. Okay, if for a surface the potential at all the points is equal or same, that surface we call as an equipotential surface. Okay, that is the definition. What do we mean? Consider you are having a single point charge. Okay, we are having one point charge. Now we know that the potential of this point charge is given by the relation 1 upon 4 pi epsilon naught Q upon R. This is the formula, right? V is 1 by 4 pi epsilon naught Q by R. Q stands for the charge. R stands for how far we are from the charge. So, if there is a surface where R is equal, okay, definitely we will say that is a sphere around this, correct? So, if I make a sphere around this charge, all the points on the sphere are at same distance from the source charge, and therefore at all points potential is going to be equal. Therefore, this sphere, this becomes an equipotential surface. Getting the idea? Okay. And you can make many such spheres. Okay. So this given dotted line, this sphere is one equipotential surface. We can make one that has a smaller radius. Now this is also one equipotential surface. Or we can make one that is larger. Okay. So due to a point charge, the equipotential surfaces, they are going to be spherical in nature. I hope that concept is clear. If we are having a uniform charge distribution on a surface, let us say we have a surface like this. Okay, there is uniform charge distribution and this is going to create a uniform field. If the field goes like this, these lines, they denote the electric field lines, correct? You can see the field is going in this manner. So the equipotential surfaces for this will have shapes like this. Okay. So for a field that is going in this manner, the equipotential surface will have a flat look. Okay. They are going to be planes in this manner. So that is the meaning of equipotential surface. Okay. Any surface where potential is same at all the points. Some things that we need to remember about equipotential surface. Okay, once again we will start with our point charge. Okay, and let us say this sphere, this is an equipotential surface. Okay, remember this is a 3-dimensional concept, not 2-dimensional. On the board we are making 2-dimensional, but it actually is a 3-dimensional sphere. Okay. So at all points on this sphere, the potential is same. Therefore, this is an equipotential surface. Now, what do we remember about this? The electric field lines that will be coming from the point charge, all these lines are going to be normal, that is perpendicular to the equipotential surface. Okay, so the first thing you will remember is for any equipotential surface, the electric field lines are always normal to the equipotential surface. Okay, it can be any kind of equipotential surface. It can be spherical in nature, it can be planar in nature. Okay, even if it is a plane equipotential surface, still the rule follows that the electric field lines are always perpendicular. That is, electric field is perpendicular to the equipotential surface. Fine, that is one thing. Second thing you will remember is, if I have an equipotential surface here, correct? There is some charge we are having on this side. Okay, any kind of small charge Q. Can be positive, can be negative. If I move the charge q from here to here, okay, if the charge we are moving only along the equipotential surface, work done is 0. Okay, you'll remember this. The work done in moving a charge along the equipotential surface is always 0. Why it is 0? Because at all the points the potential energy is the same. So even if you are moving the charge completely around, you go on moving it, you don't do any work because there is no change in the energy. Okay, so these things you will remember about equipotential surfaces. So now we will see some diagrams of equipotential surfaces. Already we have seen if you have a point charge, then equipotential surfaces are like this. Okay, they are concentric spheres. If we have a uniform electric field, then the equipotential surfaces are planar structures as we are seeing in this diagram. If we have an electric dipole, in that case the equipotential surfaces are as you see on the screen. Okay, this is a diagram for equipotential surface due to a dipole. And then next we will see if you are having two positive charges. Okay, so for two positive charges the equipotential surfaces look like this. Okay, remember whether it is two positive charges or two negative charges, the potential surfaces, the diagrams will be the same. Okay, these diagrams can be asked in the exam, okay, for 1 mark to make the diagram for a given equipotential surface. So you have to remember these as well. Now we will see relationship between electric field and potential. So I want you to look at these images. So this is the direction of electric field. Okay, it is a vertical electric field going from down to up. This is an equipotential surface A. Okay, A has a potential V. Then after a distance delta L, there is another surface B. B has a potential V minus dV. Why V minus dV? Because we are moving with the electric field. Correct? So with the electric field, the potential is going to drop obviously. So surface A has potential V and surface B has potential V minus delta V. Okay, and the distance between them is delta L. Up to here, I am sure the situation is understood. Now consider we are going to move a unit positive charge from B to A. Okay, we are going to apply some external force and move a unit positive charge, 1 coulomb of charge from B to A. In moving that charge from B to A, we will do some work. That work will be given by force into the distance delta L. How much is the force? Force will be equal to electric field into charge. Correct? If you remember the definition of electric field, E is equal to F by Q. So F is equal to E into Q. So we can get work is equal to E into Q into delta L. But Q is equal to 1. Therefore you can write W is equal to E delta L. Fine. So this is the work done, that is electric field into delta L. This work done is nothing but the difference of potential difference. Correct? So we can write this work as VA minus VB. Fine? And we will get then VA minus VB is equal to E delta L. Potential difference is equal to electric field into the distance that is travelled. Now VA minus VB we can substitute. How much is VA? VA is equal to V. How much is VB? VB is V minus delta V. Let us substitute. So I will get V minus delta V is equal to E delta L. Correct? So we'll see VV gets cancelled, minus minus becomes plus. So I get delta V is equal to E delta L, or E, that is electric field, is equal to delta V upon delta L. This is an important formula. Okay, what do we see in the formula? Electric field can be written as potential drop per unit length. Okay, delta V, the change in potential divided by the change in length. Correct? This is another definition of electric field. Correct? From here you can also see the SI unit will get delta V has V and delta L has M. So electric field can also get the units of volt per meter. Correct? So remember, for electric field, this can also be used as an alternative SI unit. This particular formula is important, okay, as it gives us the relationship between electric field and potential. So make sure that you remember this. Now for another very important derivation. Now we are going to derive a relation for potential energy due to a system of charges. Now I know in this particular chapter many times potential energy, electrostatic potential, these words we keep on hearing again and again, but I hope that you are keeping track. When we say electrostatic potential, we are referring to V. When we say potential energy, we are referring to U. Okay, so now we are going to derive potential energy, okay, not electrostatic potential. Okay, so the task now is to derive potential energy of a system of charges. So let us start with the derivation. So first imagine there is no charge present, okay, it is a completely blank slate, and then we bring a charge Q1, correct? In this particular case we are going to assume all charges are positive for now. Okay, so there was no other charge present. So when we brought a charge Q1, no work was done. Thereby, energy of Q1 is going to be 0. Okay, no work is done. Thereby, no energy change has taken place. So potential energy right now is completely 0. Fine. Then we take another charge Q2, and now Q2 will be brought over here. Now Q2, when it comes here, it has to face the electric field of Q1. Because of that, some work will have to be done, and now there will be some change in potential energy. Fine. How much will be the potential energy now? First, for that I need to understand how much is the distance. So we will make a vector and we will call that as R12. Okay, distance between Q1 and Q2 is R12. Then how much is the potential at this stage right now? For this, one simple formula we are going to use. Okay, I am sure you remember the definition of V. Okay, we have defined V as equal to U upon Q. Electrostatic potential is energy per unit charge. Fine. So V is equal to U upon Q. Therefore, you can say that U is equal to V multiplied by Q. This I want you to remember. Okay. V is U upon Q. Therefore, U is equal to V multiplied by Q. Fine. Okay. So now how much is the potential energy right now? Okay. When there are only two charges present. Okay. That is Q1 and Q2. The potential energy, let us denote it by U1. The potential energy will be equal to 1 upon 4 pi epsilon 0. How much is V because of Q1? V because of Q1 is Q1 upon R12. Correct? You remember this is nothing but V, electrostatic potential. 1 upon 4 pi epsilon 0, Q upon R12. Multiplied by Q. How much is Q? Q2. Fine. So U1, that is in this case the potential energy right now, U1 is equal to 1 upon 4 pi epsilon naught Q1 Q2 by R12. I hope this is understood. If not, rewind and once again see these steps. Okay, so this is our U1. I will call this as equation number 1. Then what we do? We will take another charge Q3. Okay, and Q3 we will bring over here. Okay, again we have to define the distances. Now when Q3 is brought here, it has to face two charges. Correct? First, Q3 is going to face electric field because of Q1, and then it will face electric field because of Q2. So once again we have to make the distances. So first distance I will make from 1 to 3. This we call as R13. Next we make from 2 to 3. This let us call as R23. Fine. So this is Q3 when it is brought over here. So how much will be the energy now? Correct, for Q3, that I will denote by U2. So U2 will be equal to 1 upon 4 pi epsilon naught. First, how much is the energy at Q3 because of Q1? It will be equal to same as before. Q1 Q3 upon R13. Right? Plus Same for because of Q2. How much it will be because of Q2? 1 upon 4 pi epsilon naught Q2 Q3 upon R23. I hope this situation is understood. Once again, see the derivation, read it from the textbook also. U1 denotes potential energy when Q2 is brought near Q1. That is potential energy U1. Then we bring Q3. Now Q3 is going to get potential because of Q1 as well as Q2. So at Q3 the energy is 1 by 4 pi epsilon naught Q1 Q3 by R13 and Q2 Q3 by R23. Therefore, the total potential energy, let us call it as U, that will be equal to U1 plus U2. Let us call this equation number second. So, substituting 1 and 2 in this. 1 by 4 pi epsilon naught will be common from all the three expressions. So, 1 by 4 pi epsilon naught. Okay, and in the bracket we will write Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. This gives the total potential energy because of these three charges. Okay, and you can find it for n number of charges. Now once again, I am very much aware that many steps we have done, correct? Many of these expressions, they start to look alike after some time. So the only option for us is to read it again and again so that we are able to make sense of this. Okay, so this expression gives the total potential energy right now. You can find it for n number of charges. The other thing to remember from this, how we brought the charges is absolutely immaterial. Correct? So when we considered, we said first we have Q1, then we took Q2, then we brought Q3. You could have started with Q3, then you could have brought Q2 and then Q1. Still, the total potential energy would have been the same. Correct? But to do that, we have to do this expression once again. Try to solve it in another manner also. Okay. If there are doubts, please don't forget to ask. If there are, we will have some. We'll try a different method to explain the same thing. Okay.